Hello everyone, this is Soham and Jagdish speaking. Right now we are going to present to you our college presentation on bioinfluence algorithm, which is made by Shubhan Singh, me, Soham and Jagdish Shukla. This is the bioinfluence algorithm which we are going to solve by traveling salesman problems using the famous algorithms like ant colony and particle swarm optimizations. Next slide. Okay, these are the table of contents that we are these are table of contents which we are put it on our presentations, such as what are influence algorithms, the overview on our traveling salesman problem, and colony optimization, its introduction and its implementation. Same for particle swarm optimization and its implementation, and the comparison between these two. Next slide, please. So okay, let's start by understanding why bioinfluence algorithm. What bioinfluence algorithms are? These are smart computer techniques that are inspired by nature, by how animals like ants, birds, or fish behave and solve problems in the real world. Instead of programming a fixed set of steps, we observe how these creatures make decisions in certain uncertain or complex environments, and we try to recreate that behavior inside a computer. Two famous examples are used here, and colony optimization, which is inspired by how ants find food, and particle swarm optimization, which is inspired by birds flocking or fish pulling. Next slide, please. Yeah, this is the features of influence algorithm. So these are the features we are going to talk about. The adaptability. These algorithms are highly flexible and can adjust their strategies on the go. Just like animals, these algorithms are highly adaptable to the surroundings. These algorithms change how they search for solutions when the problem itself changes. This is really helpful when the problem environment is dynamic or unpredictable. Next is the exploitation balance. This is one of the most important features. The algorithm knows how to balance between two things: exploration, which means searching in new or unknown areas, and exploitation, which means focusing on areas that already seem promising. This balance helps prevent the algorithm from getting stuck in a local optimum good, but isn't the best. By exploring and exploiting smartly, the algorithm can move towards the best possible answer known as the global optimum. The third feature we are going to see is emergent behavior. This refers to the idea that complex behavior can emerge from the simple rules in bioinspired algorithm. We usually have many simple agents like ants or particles that follow basic rules, but when they work together, the combined behavior results in solving complex problems. Even though each individual agent isn't that smart, the overall system becomes intelligent. Next slide, please. Okay, so now we are going to talk about the famous problem that we are going to take. It's the traveling salesman problem. So, what is this problem exactly? So, this problem we are trying to solve is called a traveling salesman problem, or TSP for short. Imagine a salesman who has to visit a list of cities. He must visit each city once and return to where he started. The challenge is he wants to take the shortest path possible. Now, with just a few cities, this is easy. But as the number of city increases, the number of possible routes grow exponentially. With 10 cities, there are over 3 million possible routes. So this makes it really hard for computers to test every single options. Uh, this is a generalized formula where you are given a list of n number of cities with a distance function of I comma j, which is representing the distance between the cities I and j. With the and we the goal is to find the permutation pi of the cities that minimizes total toll length of the at which the salesman has to travel. Next slide, please. Okay, so why is this problem so challenging? So, as I said, that there are a number of possible routes for this. Just 10 cities, we have 3 million possible routes for that, and this is general n minus one into exclamation. If n minus one factorial by two is the generalized formula for the symmetric TSP, and The second point is the exhaustive search becomes infeasible for large number of ants. So now, what are the applications of TSPs? The applications are as follows: the logistic and transformations that optimizes the delivery and pickup routes, manufacturing tool part planning for CNC machines, and circuit designs which efficient wire routing for PCB layouts. Next slide, please. Okay, so now we are going to see and colony optimization, one of the algorithms which you are taken. So let's first talk about ant colony optimization. In the wild, ants are surprisingly good at finding the shortest path from the nest to food sources. Even when there are obstacles in the way, they do this using pheromones, a chemical trait they leave behind. When an ant finds food and returns to the colony, it drops pheromones along the way. Other ants are more likely to follow stronger pheromone trails. Over time, shorter and faster paths gets more traffic and stronger trails. In ACO, we simulate this behavior. We send our vital ants across a map of cities, each takes a different route after the trip. Each ant deposits the pheromones based on how good its path was. Shorter routes gets more pheromones. Over multiple rounds, the computer starts to recognize which paths are consistently good, and eventually it finds an optimal or near optimal solution. Next slide, please. Okay, so that now we are going to see the implementation of this ACO. Now let's first understand how this works. Okay, we start by randomly placing artificial ants on different cities. Each ant will try to find a path covering all cities, just like in nature. They don't know the full solution from the start. They build it step by step. So each ant builds its route using possibility for probability rule based on two main things. First is the common trail represented by the symbol D. This stores a memory of how good a path was in previous ones. Second is the heuristic information represented by n, which is typically 1 divided by distance, meaning ants prefer closer cities. This formula shown here calculates the probability of choosing the next city. Ants are more likely to pick paths with higher hormones levels and shorter distance. The parameters of alpha and beta control how much weight we give to hormone and distance. And the summation in the denominator means we are summing all over all the possible cities the ant can go next. Now the firmware update. After all the ant finishes the tools, the firmware trails are uploaded in two ways. Evaporation, old farmers' values decreases over time to avoid over focusing on one path, and deposition. New farmers are added to the paths based on how good the route was. So better routes gets more farmers. This update process helps ants in the next round to make the better decisions. So the next step is the best route tracking. After each round or iterations, we keep track of the best route found so far. The algorithm keeps improving the best solution with it. So overall, the ACO is a powerful method that uses the collective behavior, past experience, and exploration to find a near optimal solution of complex problems. Just like the real ants find the best way to food. This artificial ants helps us to solve the tough computation problems, just like the salesperson problem. So now we are going to next slide, please. We are going to see the particle swarm optimization. So particle swarm optimization is the next algorithm which we have taken. Now this method is based on how birds fly in flocks or how fish swim in schools. Imagine a group of birds looking for food in a large field. Each bird doesn't search randomly, instead, it remembers routing. First, the best place it found food, and the second, the best place any bird in the group has found. So, based on this, the birds adjust their positions, flying closer to better areas. Over time, the flock moves towards the best food spot. PSO works the same way in computers. Each particle is like a bird. It's a potential solution. It has a position and a velocity, and it keeps moving in the direction of better and better solutions. This continues until the group finds the most optimal answer. Next slide, please. Okay. Yeah. So now we are going to see the implementation of the PSO as well. In PSO, particle represent possible solutions. In our cases, uh, routes for the traveling salesman problem (TSP). Each particle has a position which corresponds to a possible route, and a velocity which represents how its route is changing over time, sort of like the particle directions or the tendency to move. Okay, so now the updated rules to it. As the algorithm runs, every particle updates its velocity and position based on two important things. P best, the best route of this particle has found so far, its personal experience, and G best, the best route found by the entire song, a form of group knowledge. The velocity update formula shown here combines three terms. Inertia W keeps the particle moving in the same direction. Cognitive compound CR into R, CR C1 into R1, E best minus XI pulls its towards its personal best. Social component C2 R2, G best XI pulls it towards the global best. After computing the new velocity, the particle position is updated. Basically, the route gets modified slightly in a better direction. The key definitions of is this that vi is applied velocity of particles, xi is the current position, the w cic2 weights and acceleration constants. These are, and that r1 r2 are the random values between 0 and 1. So overall, the PSO balances between exploring new paths and exploiting known good ones, leading the swarm to converge towards the best possible route over time. Uh, Next slide.
Okay, so thank you, Soham. Now that we have a basic understanding about what is ACO, what is PSO, and what is our main problem, the traveling salesman problem or the TSP. So now these are the parameters that we took for our comparison. These are values that we took from research papers, and you can see them right here. There is alpha, beta, P, and Q in ACO. There is inertia, cognitiveness, social, and SOM size in PSO. um, Comparative analysis. So here we developed a small Java application that for ASO and PSO that that iterates itself, and it generates a graph whenever it finds an optimal solution or a new optimal solution. In the next slide, okay, so this is our traveling salesman problem. This is the graph. There are 64 nodes. The maximum distance is between 8 and 16. That is 894.23 kilometers. The closest node are 23 and 37, that is 3 kilometers, and the average node distance is 380.78 kilometers. So here we have two buttons, select algorithm, PSO implement, and ACO implement. So when we click on those buttons, the respective algorithm runs. Uh, yes. This is the comparative analysis for PSO solutions. So the whole PSO algorithm ran for about from iteration 1 to iteration 6,290, and it found the most optimal path and on the 6,219th iteration. Whereas in the PSO solution, it ran for about one of five iterations. On the one of five iteration, it found the most optimal path. Okay. So as you can see, the both of the iterations are running. Whenever it finds a most optimal path, it regenerates the whole graph. As you can see here, there are 10 graphs and there are 4 graphs for 8 graphs for ACO. Uh, this is the result we found. The in the first iteration, tour distance in the first iteration was 9,330 kilometers on average. Uh, Tour distance in the last iteration was 4,772 kilometers on average, or you can say 73 on average. And number of optimization is 8. Whereas in PSO, in the first iteration, the tour distance was 21,162 on average. That is way too much. That is three times more than ACO. And tour distance on the last iteration was 17,726.3 kilometers. That is more than four times that of ACO. And the total number of optimization PSO needed was 11. So there is a vast difference between ASO and PSO, as we can see. Uh, yeah, so here we're talking about observations now. We can clearly observe that the output we got from ACO and PSO has a very vast difference in them. ASO gave us the output of the total distance that we have to cover is with ACO that is 4,722, whereas with PSO we have to cover 17,726. So why that is? There are several factors like algorithm sustainability, problem representation, or algorithm suitability, problem representation, local optimal, and convergence. Let us consider these factors on basic research and research about them a bit. So the sorry, okay. So on the first slide, that is what? Okay, algorithms suitability. Uh, I'll be explaining this in short. ACO is naturally suited for combinational problem like traveling salesman problem and etc. Whereas PSO was originally designed for continuous optimization problems like tuning real world value parameters. So ASO is more aligned with the discrete and the permutation heavy nature of TSP, while PSO struggles with it. Um, to the next slide, we talk about problem representations. In problem representation, the discrete structure of TSP fits naturally with ACO mechanism, as I told above in the previous slide, that ACO is more well versed with problems like TSP, works with more well with problems like TSP, whereas PSO does not. And for PSO to work with TSP, we have to redefine components like velocity position to work on sequence instead of coordinates. So while PSO works great with continuous spaces, it becomes harder to apply and optimize effectively in discrete spaces like TSP. Um, the next slide. So, final observation. ACO finds the best TSP solution faster than PSO. As we saw, it take only 105 iterations, whereas PSO took around 6,000 some iterations. PSO runs for greater number of iteration and get better satur. It gets the best local optimal result. PSO gets the most local optimal result, whereas ACO gets the globally best optimal result. And the difference between their iteration is actually visible to us. ACO narrows down the most optimal result under 1,000 iteration and provides much faster and discrete problem solution. Handing over to you, Soham.
Okay, great. So thank you, Jagdish, for the explanation. This is the conclusion. Now, to wrap it up, the whole presentation. The bioinference algorithms are a fascinating way to solve the complex problems using the ideas from the nature. In our case, we saw how ants and birds inspired two very different solutions. And calling optimization mimics an ant behavior and performs extremely well on root problems, whereas the particle swarm optimization mimics bird behavior and is better suited for the other types of optimizations. Our experiment here showed that the ACU is more effective for the traveling salesman problem. This just shows how powerful and smart nature-inspired computing can be. Yeah, that's the slide of that's the presentation. And thank you so much for listening and seeing our presentation.
Yeah,
Thank you.
and these are the references we
That's the
took. Yeah, these are the references we took. And thank you. That's all.
thank you. Yeah.